General concepts and parts of the LiDARIT unit. The LiDARIT unit is made up of a main body, a quick-attach top plate, and a LiDAR lens located on the back. The assembly is done by orienting the LiDAR lens in the opposite direction to the drone's forward direction. The DJI Matrice 600 and Matrice 300 drones have red markings on the two front arms, indicating the forward direction. In this image, you can see the LiDAR lens, the quick coupling plate, and the side operation panel. This panel is made up of a port for power supply between 12 volts DC and 24 volts DC. There are also two connectors for the GPS antenna, each one marked on the plate with its corresponding number. The panel includes a main button to turn on the unit, a USB port to connect a flash drive that allows recording the scan information, and a micro HDMI port to view the unit's computer through an external screen connected to it, in specific cases of configuration and technical support. A screen is not required for normal operation. There is also a USB Type-C connector to power only the internal computer of the LiDAR, used only in cases of technical support. At the top of the panel are 4 LED status indicator lights. The first LED, solid yellow, indicates that the LiDARIT unit is receiving time-synchronized information, obtained from the observed satellites in NMEA format. The second LED, flashing yellow, indicates that the synchronization pulse between the LiDAR and the GPS receiver is synchronized. The third LED lights up solid blue, when the position to start the scanning process is the right one in the area where the unit is located. And the fourth and final LED illuminates solid red in the event that the unit requires technical support assistance. The next image on the left shows a front view of the LiDARIT unit from the back, performing a conventional scan at the maximum recommended flight height. The radial lines represent the LiDAR pulses emitted from the unit, creating a circle with a radius equal to the maximum range of the LiDAR. For Explorer R units, the maximum LiDAR range is 150 meters, and the maximum recommended height is 100 meters. The surfaces of the objects that are within this range, and have a reflectance property such that it allows the emitted LiDAR pulse to be returned, will be included in the recorded LiDAR data. Some surfaces have a low light reflecting ability, or reflect light in another direction and don't allow to have a scan of these surfaces, such as water, glass, mirrors, dark or hot surfaces. In the diagram, the black radial lines represent LiDAR pulses that had no return, since there are no objects within the range of the unit. The red radial lines represent LiDAR pulses that have hit a surface that is within the range of the unit, such as the horizontal surface that represents an ideal flat terrain. LiDAR pulses that impact the surface, with an incidence angle greater than 45 degrees, are considered valid data for processing. In the schematic, these pulses are shown in red. The scheme on the right shows that the LiDAR pulses are distributed in 16 channels, in order to obtain a better distribution in the point cloud. For the Explorer R unit, the channels are spaced every 2 degrees, with the first channel tilted at 15 degrees, and the last channel at -15 degrees, for a total opening angle of 30 degrees. The number of LiDAR pulses, emitted by the lens every second, is 300,000 pulses, rotating at a frequency of 10 Hz. Based on this information, it is possible to estimate a theoretical point density on the surface, which will depend on the forward speed of the LiDARIT unit and the distance to the scanned surface. On the official website, lidaritexperts.com/manuals, you will find the point cloud density calculation wizard. The fields shown in red indicate data to be entered by the user, and the fields in gray show the result of the calculation. In this wizard, the values have been calculated considering a 50% overlap between flight lines. If you have only one non-overlapping line, the calculated theoretical density must be divided by 2. In cases where it is required to scan surfaces with vegetation, there is an additional parameter to be entered by the user, and it is the percentage of estimated direct light, which is qualitatively considered, enters through the spaces left by the vegetation, and reaches the ground. With this parameter, the theoretical estimated density of points is obtained. Also available on the website is a photo overlap calculation wizard. The fields shown in red indicate data to be entered by the user, and the fields in gray show the result of the calculation. These input data are camera resolution of 12 megapixels for LiDAR units, height of flight, distance between lines of flight, camera angle of view of 87 degrees for LiDAR units, speed of flight and the time interval between consecutive pictures. With these input parameters, the wizard calculates three values: the longitudinal overlap, the lateral overlap, and the pixel size on the ground. It is recommended that the longitudinal overlap of the photos be greater than or equal to 80%, and the lateral overlap of the photos be greater than or equal to 60%. The photos taken by the LiDAR unit are used to generate a reference orthophoto, which allows viewing small objects that, due to their size, are not visible in the digital surface model. This orthophoto is also used to add RGB color to the point cloud. If the ultimate goal is to obtain a conventional orthophoto, a flight other than the LiDAR flight should be considered, increasing the longitudinal and transverse overlap. Whenever possible, use checkpoints. In cases where control points are not used, the orthophoto is adjusted considering only the common visible objects between the digital surface model and the orthophoto every 50 meters on average. If you have dedicated equipment for photogrammetry, you can send the images taken by the dedicated equipment for photogrammetry to be used in the process of creating orthophoto and point cloud colorization. The result of this orthophoto will depend on the equipment dedicated to photogrammetry, and on the adjustments made by the operator during the data collection. LiDAR, digitizing the world.